It's time to study another family of surfaces, a family known as the quadric surfaces. And as we study these, you'll need to hearken back to your days in pre-calculus, and maybe even before that when you studied conic sections. And remember with conic sections, what you did was you learned about parabolas, and this is just a basic parabola here, y equals x squared. We learned about ellipses. This is just a basic ellipse, and hyperbolas. So we studied these conics, and when in studying these conics, basically what we were doing, we were recognizing the form of the conic, recognizing this is a parabola, this is an ellipse, this is a hyperbola, and then we were uh, investigating various characteristics of those conics. And in particular, we learned that generally a conic section is algebraically could be written this way: ax plus bxy plus cy squared plus dx plus ey plus f equals 0. Yeah. And we said, okay, this is the general form of the conic. And if you're given something that looks like that, you were able to manipulate it, probably using completing of squares, and get something that was in a form that you could easily identify the characteristic parts of the conic. Well, now we're going to kind of go to the third dimension. So these were things that we investigated in the plane. But let's think about what would happen if we had, like, maybe instead of y equals x squared, let's suppose we had something else. Let's suppose now that we have three dimensions, we have z equals x squared plus y squared. That's different. It kind of looks like a parabola. If we just had z equals x squared, we would have the z-axis here, the x-axis here, and then it would just be a parabola. But that's not what we have. We have x squared and y squared. So what we want to do is we want to say, okay, well, what does this look like? Because now we have these three variables, not just x and y, we have the z. So let's think about this. Let's think about the x-axis and the y-axis. In other words, I want to investigate what this shape would look like just on the plane. In other words, if z is equal to 0. If z is equal to 0, let's see what this looks like. Well, if z is equal to 0, you have x squared plus y squared equals 0. Well, that must be just a point, right? It's just a point here. That's all that is. Okay, so on the xy plane, you've got a point. Now, so let's back up a little bit. Suppose you're standing above the xy plane at z equals 1. Okay, well, what do you have now? X squared plus y squared. Okay, on this plane, z equals 1, what does the shape of this look like? What do you have here? Well, you have a circle, clearly, right? So it's got a radius of 1. So if you're looking, maybe I can make this look a little more accurate. There it goes. So remember, you're standing above the plane. Above the XY plane, and you're looking down, and there's what you see at z equals 1. Yeah. Now, let's suppose you have z equals 4. So you have x squared plus y squared equals 4. Now, look, these are all curves, and they're all in a plane parallel to the XY plane. So let's just look and see what this looks like. So we move up here. We have a circle of radius 2. There it is. Yeah. Okay. So there's what it looks like for z equals 4. See, now remember, you're looking above, and we're just looking at part of these. Now let's suppose z equals 9. What do you have? Well, So look, you have a circle. There's a unit circle. There's a circle of radius 2. There's a circle of radius 3. So you're looking above. You're above the XY plane, and you're looking down, and here's what you see. You're seeing all these little curves. Okay? And these are all in planes. This one's in the plane z equals 9, z equals 4, z equals 1. And they're coming up toward you, right? You're looking down at them. And the question is, and now we just did this for z equals 1, z equals 4, and z equals 9. There's infinitely many values of z between 1 and 9. So think about this as kind of a like a shell or like a I don't know, a structure. And there's lots missing in between. So you can think though, if we let, for example, z be 1.01, we would have another circle down there. In other words, there's infinitely many circles. And the question is, well, what kind of shape would that form? That's the question. Okay. Now, let me just say this. Notice that these little circles all are part of a plane. Okay. So they're on a plane and they're parallel to the XY plane. Now, this surface that we're talking about, this surface right here, this surface, we don't see the whole thing there, but these circles are all on planes that intersect this surface. Okay. So if you look at this surface, these are all representative of the intersection. So this this plane z equals 9 intersects this surface right here. Z equals 9 intersects this surface with this curve right there. So these circles are called the trace of the surface. The trace of the surface. That's what these circles are. It's where the plane, these various planes intersect with the surface. Now let's take a look at what this surface would actually look like. Okay, here is what it looks like from above. So we're looking down at this surface. We've got the red axis is the X, the green is the Y. Now let me just spin this around a little bit so we can see the whole thing. There it is. There's what it looks like. And you can see this thing is formed by a bunch of these circles being stacked up here. Yeah. So in 3 dimension, this is kind of like a parabola, right? But we're not going to call it a parabola. We're going to call it an elliptic paraboloid. So let me write that down. Elliptic paraboloid. Yeah, there it goes. An elliptic paraboloid. Now, the standard form for an elliptic paraboloid would just be x squared over a squared plus y squared over b squared. Okay, and it doesn't have to be z equals. Notice that with this one right here, all of our traces parallel to the xy plane are circles, or we could modify it and make it an ellipse. See, the example we looked at, a squared and b squared are just 1. Okay, but this is how it could look. Now it could also be this way. It could be x equals y squared over a squared plus z squared over b squared. It could also be y equals x squared over a squared plus z squared over b squared. But these are all, this form right here, that's what we call an elliptic hyperboloid. Elliptic hyperboloid. Okay, now let's keep on investigating this z equals x squared plus y squared. Let's keep on investigating that a little bit longer. Let's suppose that we set x equals 0. So if x equals 0, we have z equals y squared. Okay? So let's see what this looks like. So we have this plane here now. Here's the plane. We have y and we have z. And here's what this looks like. Okay. Okay. So this is a trace also. And for this particular trace, these, now notice we don't have to have x equals 0. We could say this. We could say, well, let's let x be 1. Okay. And then we would have z equals a y squared plus 1. So we would have a parabola that looks up like this. The thing is, with these, our traces are not circles. Okay. So on this other one, notice our traces were all circles. That's when we were just adjusting the z. In other words, parallel to the xy plane, our traces are circles. But what about if it's parallel to the YZ plane? Okay. Notice I let x be 0. Now we're dealing with the YZ plane. Parallel to that plane, we have parabolas. Okay. Notice we're parallel to the YZ plane here, so we have parabolas. Okay. Now, think about this. Let's look at it again. Let's suppose we've got y equals x squared plus y squared. And now let's let z be 0. Now what plane are we dealing with? Well, we have the x and the z plane. And now we have something that looks like this. Now, if we let y be 1, we've got z equals x squared plus 1. Now, these are traces. These are traces that are parallel to the now the xz plane. And notice those are parabolas also. Yeah, these are parabolas. Okay, so let's build on this a little bit. Let's look at another uh, let's look at another one of these. Let's suppose we have z equals x squared over 4 plus y squared over 9. Let's think about this. Now, we're given this quadric surface. And here are the questions we want to answer. We want to answer questions about the traces. Okay, the traces. Now, I'm going to start off looking at the trace when we adjust the z's. So think about this. So think about it, we're just looking at parallel to the xy plane. Let me put this over here, plane. Okay, so let's look at the traces parallel to the xy plane. Well, I'm going to let z be 0 to get that. I'm going to let not just 0, I'll let it be several things. So I've got z equals 0, and I've got x squared over 4 plus y squared over 9. Well, that's just a point. So you're looking at a point, the origin, right? Now, let's suppose we let z be 1. Well, if z is 1, you can see what happens here. You've got an ellipse. Yeah. So at z equals 1, parallel to this xy plane, you've got an ellipse. And it doesn't matter. I could change this. I could say, well, what about if this is 2? Well, you've got x squared over 4 plus y squared over 9. That's still the form of an ellipse. You know, it would look like this. It would be x squared over, well, let me this way. You would have 1 equals x squared over 8 plus y squared over 18. Still, that's an ellipse. So in the traces parallel to the xy axis, you have an ellipse. Yeah, actually, I got some misspelled ellipse here. Okay, there we go. Ellipse. Okay, now let's look then at what about parallel to the uh, let's say xz plane. Okay, we're looking at xz plane, then that's when we're going to let y be 0. And we have something like this. We have z equals x squared over 4. Well, right away, you recognize that as a parabola. So if you're talking about the xz plane, you have parabola. There we go. And then you can say, well, now I want to do the yz plane. Well, same thing. You would have z equals y squared over 9. And then you could adjust the x's, but that's still going to be, if we're talking about the yz plane, that's still going to be a parabola. Yeah. So you've got these three traces that you're concerned about for this elliptic paraboloid. Okay. Now notice we recognized it was an elliptic paraboloid just by the form here, right? Notice the only things we had z which was not squared, the x was squared and the y was squared. Now we want to investigate these quadric surfaces generally and not just this um, elliptic paraboloid, but in general. So let's look at that. So here is the general form for these quadric surfaces. And you notice, yeah, it's a little more complex. Well, it's a little longer than for the conics because you brought in another dimension. So yeah, it's going to be a little more involved. But let's, of course, if we see something in this form, it's kind of hard to tell much about it. What kind of surface is it and whatever. So remember, just like with dealing with conics, we want to use our algebraic tools, our tools of algebra, to manipulate it, to manipulate our expression so that we get something that we can work with. So let's look at an example. Okay, let's look at this one. Let's suppose that we've got 4x squared minus 4y plus z squared equals 0. And we want to see if we can figure out what kind of surface is that, and we want to make a determination about the railings. We want to get an idea about what this might look like. Well, I notice, first of all, I've got an x squared and a z squared that are both positive, and then I've got this negative y. So here's what I might want to do. I might want to see if I can put it in the form that we worked with previously. So I have 4y, just move that to the other side. I get 4x squared plus z squared. See? Now divide through by 4 and look at this. We've got x squared plus z squared over 4. Ah, that is an elliptic paraboloid. We recognize that right away because it's of that form. We have y equals x squared plus z squared. And there's a constant involved in 1x squared plus 1/4 z squared. Now, okay. Now we recognize, okay, this is an elliptic paraboloid. Now let's start talking about the traces. Let's look at first of all, let's look at the xz trace. Okay. So what we have then is I'm just going to put a 0 in for the y. And now look what we have. We have uh, x squared plus z squared over 4 equals 0. Now I can adjust that. Let me make it equal to 1. And then I have this. I have x squared plus z squared over 4 equals 1. Ah, see, so we had a point here. And here you start to see, oh, we've got an ellipse. Now, as we go down the y-axis, as we move along the y-axis, we see that we get a bunch of these ellipses. So we get x squared plus z squared over 4 equals, let's say, 3. Okay, just divide by 3, and I got x squared over 3 plus z squared over 12 equals 1. Ah, clearly, that's an ellipse. So if we're talking about the traces parallel to the xz plane, then what we have is we have ellipse. These are ellipses. Okay, no question about it. Okay, now let's look at the YZ plane. Okay, YZ plane. And let me change colors here. Okay, if we look at the YZ plane, now we have, uh, well, I'm letting the X be 0. And that's clearly parabola, right? We could add in various X values, but you can see those are just going to, as we move down the the X-axis, we just get parabolas. So these are going to be parabolas. Parabolas. I don't know what's up with my spelling here. Parabolas, parabola. Okay. And then we've got the the YX or XY plane. Okay, the old familiar XY plane. And there we have y equals x squared. Well, that's a parabola. Yeah, there we go. So now we know this is the important information. So now we want to put it together and we want to sketch get a sketch of it. Now, I'm not the best at sketching three-dimensional uh, uh, surfaces. However, I can sketch, some basic ones. I could probably sketch this one okay, but I want to show you how to use GeoGebra. So let's look at that. So what you want to do is you want to go to geogebra.org/3D. So GeoGebra, GeoGebra.org/3D. So let's look at this one that we just sketched here. I think it was y equals x squared um, plus z squared over 4, I believe is what it was. Yeah, there it goes. So there you can get a good view of what the graph looks like. There he is right there. Now we can turn on axis on this, or we can turn on labels. Notice I can go over here to settings, go to the tool of the gear and do settings, and I can name the axis. So I've got the x-axis, I can label it X. Got the y-axis, I can label it Y. And the z-axis, I can label it Z. Okay, and then those, yeah, see there, now they've got the labels on them. Okay, there's the z-axis. Now the elliptic paraboloid, that's not the only quadratic surface, of course. We've got others. Let's just take a look at some of these. This is an ellipsoid. You can see where it got its name from the ellipse, right? But we're generalizing. We're saying, okay, in 3 dimensions, what does it look like? What would we think of as something that corresponds to an ellipse? Well, an ellipsoid. And notice we've got this, just like the ellipse would be x squared over a squared plus y squared over b squared equals 1. Now we have the z squared over c squared. So you can see the various traces there. Okay, so you want to get these locked into your mind so that you see this and you're thinking, okay, that's an ellipsoid. Notice these are all positive. The x squared is positive, the y squared is positive, the z squared. All those terms are positive, equaling a positive number over here. So remember that, and you can lock it in, kind of thinking about it as an ellipse and what you know about the ellipse. We've got the hyperboloid of one sheet, and notice you've got one minus there. Notice the x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. Now remember, an ellipse, a hyperbola in the plane, we just had something like x squared over a squared minus y squared over b squared. Now we've got, look, this term is positive, this term is positive, then minus one of these square terms, right? In this case, z squared. Notice the 1 minus, there's one of them, hyperboloid of one sheet, okay? So far, so remember, we've got the ellipsoid, We've got the hyperboloid of one sheet. Now let's go on over. Now notice the hyperboloid of two sheets. There are two negative terms, right? See what that looks like. Okay. Hyperboloid of two sheets. They look very similar. Elliptic cone. Okay. Now notice this looks a lot like a hyperboloid of one sheet, right? However, it's not equal to 1, it's equal to 0. Okay. So if this was x squared over a squared plus y squared over b squared minus z squared over c squared equals 1, well, that's your hyperboloid of one sheet. But this is a cone. It's got a 0 there. We've got elliptic paraboloid. Okay, so we're familiar with that one. And notice the general form there. And then we've got a hyperbolic paraboloid. So notice we've got a couple of paraboloids, right? We've got the elliptic paraboloid and we've got the hyperbolic paraboloid. Now remember, the elliptic paraboloid has a plus right here. The hyperbolic paraboloid has a minus. So that's pretty easy to remember if you kind of relate it back to what you know about hyperbolas and in the conics and the ellipses in the conics. Okay, so it makes it a little bit easier to remember.